So actually, I'd like to go look at some experiments on MBL in 1D and 2D and the ways how we probe this and the limitations also of the experiments. And then I come to this question, which actually Dennis actually already yesterday started touching upon, which is super important for any experiment, but interesting by itself. You know, what happens when you couple MBL to a bath. And actually, I don't want to consider a huge bath. I also want to ask the question, what happens if you have a finite bath, something that is not huge, but that can be affected in principle by the other component. I think it's a very interesting question. I think still a little bit open question, but talk about that. And if time permits, we can also talk. I'd like to show you some very nice experiment from Markus' group in Harvard on actually how you do the opposite, how you actually show that something thermalizes. Before we're going to show that something does not thermalize, but actually I want to also show you how you show the opposite, which is actually, it turns out to be a little bit harder, I think, than showing the first thing. All right, so I just repeat a little bit the folklore of MBL, that we're basically looking for the absence of thermalization. So indeed, we're going to follow this recipe that has also worked very well for the Anderson localization case, or in our case, what you see here on macroscopic objects. You just prepare something that is an obviously non-equilibrium state, your coffee, cappuccino, latte macchiato served like this, and of course it will evolve into this. And if it does not, well, then you can have some evidence that the system has not thermalized, at least for the time scales you're looking at, right? It is not in thermal equilibrium anymore. So in a quantum system, a similar thing happens. Basically, you can think of, you know, all these quantum correlations that build up in the local degrees of freedom are rapidly lost as the system gets entangled with everything else in the system, and then typically we have classical hydrodynamic description, which can give very efficient description of the slow mode evolution in the system. And MBL, of course, is a nice example where this actually does not happen, and actually where the statistical physics approach fails, and I think that's why it, of course, generated so much interest. Yeah, also what was shown to you in Dima's talk and Dennis' talk, just again to rephrase it in my own words, basically if we think about thermalization of an isolated pure system, you know, this is conceptually an interesting question, because usually when you think about thermalization, you always think about it in the context of being in contact with a thermal reservoir. But let's imagine there is no thermal reservoir. Let's just imagine this is a pure state. This is the entire system, and this is a pure state of the entire system. Then it turns out, if you look at a subsystem, which is not large, which is small compared to the entire system of that, and you look at the typical physical system and look at the subsystem, and you calculate the reduced density matrix for that subsystem, you actually find that that's pretty well described by a thermal density matrix. Okay, and so everything in here is a thermal density matrix, and people then often say, well, the rest of the system acts as a bath for this subsystem A. Yeah? And that's what's typically true, and then the von Neumann reduced entanglement entropy basically is the thermal entropy of the system. Okay. Now the scenario, of course, we're interested here is where this does not fail, where this would be volume law entanglement, and we've heard from Dima's talk that in the MBL systems actually turns out we get this area law entanglement. So there's a different scenario for the system, and we're looking for cases where this fails. And you heard, of course, that in this disordered systems with interactions, you can have that, and these prototypical spin systems are good cases to study that. And you can write down these kind of local integrals of motion as basically these L bits that are emergent features, emergent kind of bits, quantum bits, qubits in your system, which are basically dressed physical bits. So they are kind of you know, linear combinations, unitary combinations of some of the physical bits surrounding, you know, this central bit here. This would be the dressed L bit picture, and would be the conserved quantities in your system. And then you can write down basically this emergent integrable model for the system, which gives rise to MBL and which shows also this entanglement dynamics that you've heard about. All right. There's been a lot of theory, I mean, a huge amount of theory work on this. There's been much less experimental work on this. And I think Cold Adams started this, but by now there's also some work on ions and V-centers and electronic systems. The challenge is, as we'll see, is that for any experiment you have to be able to go to long evolution times. I mean, this is already true for the Anderson localization case, but this is also true here for the MBL case. If you want to say something, you really have to be able to push to long evolution times and do that in an isolated system. You're not allowed to have coupling to the outside world, no decoherence to the outside world. And that's, of course, challenging to do that. All right. So important points from an experimentalist, I think we will try to address also. There's very little theoretically known about MBL in dimensions larger than 1. I think most people would say it's unlikely to exist right now because of instabilities. But I would say the situation is a bit unclear. I'll just show you the experiment, and you can take from that what you want. So I'll just show you the experiment. And also it means, of course, we need to precisely characterize the experiments, and I'll show you how to do that, and also the disorder landscape. And we really want to have the systems isolated from the environment. And no experiment is completely isolated from the environment. It's just never going to happen. So this is an idealization which no experiment can ever reach. And so we're trying to push this to the longest possible times. In our case, this would be around 1,000 internal dynamics timescales, whether that's the hopping or the exchange coupling, whatever your typical timescale is. For us, it would be the hopping. So this limits our observation time. So everything that I will tell you is always limited to this time scale. I cannot say you what's going on beyond that. So if you have a theory that tells me that after 1 million t or 10 million t something's going to happen to the system, I won't be able to check that. At least we in our experiments, maybe somebody else can, but that's something where experiments are limited. So I guess, because you're always coupled to the outside world, that's something one always has to take into account, and this is why it is important to understand how coupling to the baths actually can affect experimental signatures. Okay, so we've already heard from Vincent the beautiful work in Paris on Anderson localization, so I don't have to talk about that a lot anymore. I just want to give the spirit again. You just prepare an initial state, you evolve it, and you try to see what happens in the system. And the simple experiment idea actually also works quite well for MBL. And this is what was put up also yesterday by Dennis. This was our first experiment in the field, which was without quantum gas microscopes. It was basically putting fermions, Fermi-Hubbard model. So you have fermions in the system, 2 spin components. You have interactions between the fermions. You can tune these interactions with a Feshbach resonance. So we can nicely always compare to the non-interacting case and compare to the Anderson localized case. And then we can change interactions and see how the behavior changes as we add interactions to the system, keeping all other system parameters the same. Okay, that's really an A-B comparison. We can keep the quasi-periodic potential that you see here that we're going to be using in the Aubry-André model the same. The tunneling matrix elements will be the same. The only thing that's going to change is the interaction. And then we can look how observables change. Okay. So we have this Aubry-André model, and for the Aubry-André model for u equals 0, actually we know, of course, everything or a lot about this model. We know that all eigenstates are extended for delta over J, where J would be the kinetic energy of your particle smaller than 2, and all eigenstates are exponentially localized for a delta larger than 2. And this is what you can see here. So for example, I plot you the wave function weight on the different lattice sites, for example, here as a function of the disorder strength. And you can see you have these extended wave functions for low disorder. And as soon as you cross this 2-point, kaboom, this goes into the exponentially localized wave function. And this is a transition here happening exactly at delta equals 2. And you have this kind of logarithmic kind of divergence of the localization length at this transition point. Here you have an Anderson insulator, and here you have a metal. Now, of course, in a trap that has been talked about a lot, these traps have been imposing problems, but I've shown you yesterday there are now new ways how to get around the trap by making really box potentials which don't have this harmonic confinement problem. But if you do have a trap, and some of the experiments are affected by this, as they were the first ones and had this trap, then you can expect this divergence to be rounded off, so it will kind of a crossover if you go into a trap. So keep that in mind. So this is how the trap typically changes these pictures. You cannot have this divergence here at this, only up to some scale at this disorder strength. Okay, so now let's do the experiment. So what we do is we prepare an initial state, an out of equilibrium state, like this coffee and milk mixture. And in our case, a nice way to do that, to prepare this state, was this kind of even odd staggered charge density wave state, where all the even sites are populated and the odd sites are not populated. We do that, we like this state because this allowed us in the first experiments without quantum gas microscopy to read out this imbalance in a very efficient way. We had very nice ways to probe the population of the even sites and the odd sites independently. And then you can just introduce this variable, which I think the community has now widely adopted in looking at the dynamics. We call it just the imbalance of this charge density wave. It's just basically the visibility, the contrast of this charge density wave. It's just the number of particles on even sides minus the number of particles on odd sides divided by the sum of the two, okay? And if that's 0, then all sites are equally populated and you have no memory anymore of the initial states. And if this imbalance is finite, then it means there is some memory of that initial state at that time scale that you're looking at, okay? Now, when you look at the problem, what do you know with interactions? Well, we've heard about the non-interacting case. I just talked about that. Everything's understood. We know there's Anderson localization at this critical point of delta over J2. Actually, we also know in the U equal infinity case, we also know the answer. Because when we have infinitely strong repulsive interactions and no doubly occupied states in the initial occupation of the system, then we can map the system again onto free fermion case. And there also we know it should be exactly Anderson localization. So this is also exactly known, this point and this point. So this we know. So now you can already kind of suggestively draw what the thing might look like in between. Well, interactions typically, as Thierry told us, tend to delocalize you. So you might say, okay, if there is localization, it might happen at a stronger, would have to happen at a stronger disorder strength. So this would push my kind of localization transition here up. But then I have to eventually go down again to reach this point. Okay. Now, it could be, of course, more complex things going on between, but this is kind of the simplest guess how this thing would look like in the experiment. So this is how we do the experiment. Then we prepare this charge density wave, we evolve in the disorder, and then we read out the charge density wave and to see what it is. And here's these first results that we had in 2015 on this imbalance, where you see, like, for this interacting system, different interaction parameters, where we can see that as a function of disorder strength in the system, if there's no disorder, then basically you just relax to 0 imbalance. If there's finite disorder here, you see how you cross to these values here, where you get this finite steady state imbalance at this evolution times of about 30 or 50 tau in this case. Okay, just to show you that interactions actually have a dramatic role on the system, really have a huge role, I just want to show you some unpublished experiments from 2D quasi-periodic. So we just take a 2D quasi-periodic potential and put non-interacting particles into them, and we expect Anderson localization, and that manifests itself as a finite imbalance for long evolution times. So there's an initial relaxation of this charge density wave, and then it settles into the localized state. So this is this finite imbalance that you get for the Anderson localized state. And then for the same parameters, actually, you just crank up the interactions to about 5J, and you see how this this basic localized state just decays. So there's no localization anymore there, just decays. Everything else constant. Really very dramatic effect, just adding mild interactions to the system, you immediately see how this completely decays. Just to check for us, reference check, I always said the U equals 0 point is a good reference point for us to check compare to. So you see actually when we compare to the exact diagonalization results for our system, including the trap, we see that the imbalance we measure in the experiment for long evolution times for the non-interacting case actually very nicely follows the exact result. And that's just, again, a good cross-check for us that we know what we're doing in the experiment. Now we add interactions to the system. And indeed, we see something very much like this suggestive picture I drew before. So you see here, as a function of interaction strength, so 0 is the non-interacting case, vertical axis is the disorder strength, and in color, I just plot this steady state imbalance after this long evolution time. So you see there's the case where we have 0 imbalance, where basically the system is ergodic and thermalized, and then very suddenly the imbalance starts to rise to finite values, and this is where we would say there's this MBL transition happening. And then we can look at the shape of this contour profile and plot it, for example, here in this case. And you see it has this characteristic W profile that actually also makes sense. I'll explain to you in a second. We understand quite a lot about it. So there's the non-interacting case that you can see here. And then for positive or negative interactions, there's actually in the Hubbard model, there's a dynamical symmetry which has to, by which you have to have symmetry on this axis for positive and negative interactions. So it doesn't matter whether you have attractive or repulsive interactions in the system. And this gives you this W shape. So here you would say, okay, you're localized more, but in order now your localization, your imbalance decreases with interactions in the system. So in order to localize it again, you would have to go to higher interaction strengths, which you can see in this 2D plot. So you can also interestingly compare this W to numerical results, and you heard about this logarithmic growth of the entanglement entropy. And it turns out that this minimum in the imbalance that I showed you before that we can measure in the experiment actually very nicely corresponds to the maximum in the slope of this linear growth of the entanglement entropy. Okay, so we can do this for different interaction strength in the system. We get different slopes here for the log t growth of the entanglement entropy, and this is just kind of the opposite of what we see in the imbalance of what we see in the entanglement entropy growth. Let me come back to the point, if we have no doublons in the system, remember I told you that the U infinity point should be again like Anderson localization, like the non-interacting point. And this we can also check. We can prepare an initial state that has no doubly occupied sites initially. We start with a non-interacting case. We see localization, some infinite imbalance after some evolution time, long evolution time. And if we go to infinite interactions, well, infinite for us is maximum of 20, but that's pretty strongly interacting case. We see we indeed recover exactly the same point as we do here. Okay. Interestingly, when you add doublons to the system, that's not true anymore. If you add many doublons to the initial state, you actually find that you need much larger, you can actually localize the system already for much lower disorder strengths, or you get a higher imbalance, which you can see here for the steady state imbalance. But this is something we can also very nicely understand, because if you have these doublons, these interacting doublons in the system, their kinetic energy is not the bare kinetic energy of your problem, but they hop as pairs, as correlated pairs, and their kinetic energy is J squared over U. And if J over U is large, then this is much smaller than the original kinetic energy. So they just have a much smaller, the doublons have a much smaller kinetic energy than single particles. So in order to localize them, we need a much lower disorder strength to localize them. Okay, so it also makes sense that we see here if we pair these different initial states in the system. And again, positive or negative interactions doesn't matter. You know, these doublons hop if you have attractively interacting doublons or repulsively interacting doublons, they're the same. All right, let me go to the 2D case, which is much more contentious, I would say, but let me just show you how we do the experiments. So in our case, we don't use a speckle pattern. We actually use a disorder pattern that we can project through this digital mirror device that I showed you in the lecture yesterday onto the atom. So I showed you how you can make nice boxes, wires of light, different lattices, but of course you can also make disorder. Right? You can do whatever disorder you want. You can just program onto this digital mirror device and project it onto the atoms. And that actually gives interesting possibilities that I'll talk about actually in a second. And we can measure, for example, the probability distribution of this disorder strength. It has a Gaussian shape centered around some average kind of disorder in the system. Now, just to show you how we characterize this disorder, that we know what we're doing, and making use now of the local control that we have in the quantum gas microscopes. Imagine this is the disorder that you have on your digital mirror device. You project that onto the atoms, and the objective has the effect of blurring everything a little bit. There's a finite resolution of the lens, so it's just going to blur the thing a little bit. So you go from this clear picture to this slightly blurred picture, and this is what you expect. Okay, this is calculated. But now we can also measure this, because I can go into the lattice and making use of this tune-out trick that I'll come back to later, this spin-dependent potentials, I can make local spin flips, exactly what Vincent was showing you, transfer one spin state into the other system, into the other spin state, and that of course will now be dependent on the transition frequency, and that will depend on the disorder strength on the lattice side. So here now I measure the transfer map, spatially resolved now, given my calculated disorder potential, and you can actually see we nicely see the features that we measure and what we expect. So we expect, for example, this ring here. You see this ring over here. we see this line here, you see this line over here, this blob here corresponds to this blob. So just to show you, we don't have to rely on calculations. We can really measure the disorder pattern and perfectly characterize it in that way. Okay. So this is how we characterize the disorder, and we can actually tell you also what the correlation length of the disorder is in the system, and calculate that. Just to show you, so far in this experiment we're using true random disorder, but you could also use the 1D quasi-periodic, what we've been using before, and they give you, just for those who've never seen it, you know, in terms of probability distribution of energy shifts, they give completely different types of disorder, of shifts in the system. So they are very different, although we understand they sometimes give rise to similar physics. Yeah, just they can be very, very different. Yes. Yes. That's a bit more tricky, but there are ways going from higher dimensions to projecting onto lower dimensions doing that. That's what Uli is doing in Cambridge. Yes, yes, yes. Yeah, then of course, if you program it in, then you could do that, of course. Yes, that's right. But not with a simple, just other incommensurate lattice. All right, so what we're going to do now in the experiment, again, we're going to start with some recognizable density pattern, which is the initial state where we know this is not a thermal state. And we just let it evolve until we believe that some steady state is reached. And you know, then we can analyze this remnant pattern and say if the system is localized at this point, if there's evidence for localization at this point or not. Okay, so again, we started doing this now with a 2D case system. Now again, Hubbard model, but in this case, Bo's Hubbard model. We have this now real random disorder in the system. As you can see here, we have the interactions between the particles and we have the kinetic energy. And the system that we looked at first was this domain wall. So we prepared in a trap with this lattice potential and the disorder. We prepared everything to the left here occupied and nothing to the right occupied. And this is a picture you can see here. So this is the system that we had been preparing at that point in time. So it's quite a bit smaller than what we can do now. If you compare to the pictures I showed you yesterday, they're order of magnitude 10 or 20 times larger than what we could do at this time. So I think it's worthwhile going also back to these experiments. But they show the idea. So you start with this half moon. This is a single snapshot. This is average over many snapshots. And then you let the system evolve, and you see in the case without disorder, you see just that the system just expands into this other half region of space, and then eventually just becomes a symmetric distribution as you would expect for a thermalized system, which interactions thermalize the system, and you get your mixed coffee and milk basically here, where everything is basically in the symmetric distribution. But now if we add interactions to the problem, we can do the same thing, and you see actually after long evolution times, you now see that it does not evolve anymore into the entire system, and in fact it seems even it stops at evolution at this very long evolution times. And we can plot that now, quantify this by again introducing the imbalance, which now I would just call the particles to the right of the domain wall minus the particles to the left of the domain wall, and divided by the sum of the two. And I look at the evolution of the imbalance as a function of time, here up to 300 evolution times. And you see if there's kind of weak disorder or no disorder, this very quickly relaxes to 0. But when there's disorder present in the system, it kind of seems to settle into the steady state value that you can see here. And actually, if we look at how this imbalance evolves as a function of disorder strength, you see actually that it seems to be 0 up to something like 5 or 6 in units of J, but then very suddenly seems to rise. Okay? There's another way how we can probe that. Remember, we had this domain wall that we were looking at, and we can fit the density profiles of this domain wall in this right half of the system, and they turn out to be actually quite good exponential decay profiles. So this is the normalized density to the right of the initial domain wall, and you can see actually that they follow very nicely on this log-lin plot linear curves. So we can fit some exponential decay, a decay length to that. That's just experimental way. I don't know how that relates to the Elbit decay length or to the Anderson decay length. But this is just a way of measuring that experimentally. And then we can also see that indeed this decay length seems to diverge here at this transition point of around 5. Okay, just another way of analyzing the data, showing that something is happening here, seems to be happening here. One way, just again to check whether we can recover Anderson physics. Unfortunately, in this experiment, we don't have a Feshbach resonance, so we can't tune interactions to 0 like in the first experiment, but we could dilute the system. And by making the system in 2D more and more dilute, you expect also to go back to the Anderson limit. For an Anderson local insulator, remember in 2 dimensions, arbitrary weak disorder already localizes the system. So in terms of the imbalance, you actually expect the imbalance to immediately become non-zero once the disorder is present in the system. This is what numerics tells us. This is what this curve is, the squares. So this would be the numerically calculated imbalance for our system as a function of disorder strength, and you just go immediately up, okay, for arbitrary small disorder in the system. Now here's what the experiment I showed you, the experimental data I showed you, the light blue data, which showed this kink around 5, 6. And now we can just dilute the system, make it much less particles in there. And by diluting it, you effectively go to lower interaction strengths in the system. You more and more recover the Anderson limit. And indeed, you see how this transition point now seems to shift to lower disorder strengths. And the expectation is, of course, if you would indeed go to very, very dilute systems, it would just push all the way here and become this curve. Okay, but still it looks very, very different from what we see in the Anderson case. Yes. Yeah, this was done. We can revisit all those questions. I don't have an answer for that. So one can do this now much better. I showed you yesterday with this much larger homogeneous systems. We can also do really system size scaling. I think there wasn't really much dynamic range in the system sizes we had available at that time. Okay, but I think it's indeed worthwhile going back to that question, looking at system size. But there's no numerics on this, so nobody can calculate this. So it would be indeed interesting. Let me just show you another interesting setup. You might say, well, this domain wall is maybe special. You're expanding into vacuum here, so maybe that's actually a special situation. Let's just use a different situation where we use this stripe pattern, for example, as an initial state that we want to measure and look for localization in the system. So we can do exactly the same experiment. We can measure the imbalance as a function of evolution time, and this is the data that you can see here. So this is imbalance as a function of evolution time for this different kind of charge density wave now that we also had in the Aubry-Andre case. In the 2D case, and actually you see that this imbalance seems to saturate very nicely to a steady state value up to very long evolution times of 1000 tau. Okay, so if we fit that, we see a very fast relaxation on the initial timescales of just a few one hopping, which is basically just the timescale to hop into this empty space. Okay, there's nothing interesting about that. Then there seems to be another timescale of about 100 tunneling times, which is associated with this decay here. This is absolutely non-trivial, and we don't know where that emerges from to calculate that. And then we can put at least an upper bound. If you would say, what's your upper bound that this is also not decaying just very slowly? I mean, it could be extremely slowly decaying also. And our upper bound for this final decay time here is about 2,500 tau. But as you can see, I think it's pretty good evidence that it seems to be settling in. And if there is relaxation, it has to be a very, very slow form of relaxation. And again, at those time scales, we again cannot be sure if this relaxation would be caused by coupling to the outside world or is something that's intrinsic to the system. Okay, but I think it's very, very interesting data, and again, worthwhile repeating with the better systems we have now. But I think already, this is very strong evidence that there is something related to localization in these systems. Maybe not in the infinite size system, but at least for the system sizes we've been looking at there. Okay, yeah, some quick questions. How am I doing in time? Okay, good. So just a few quick questions I want to throw up because I think they're interesting to look at. We heard a lot about the resonances and avalanche instabilities already that could destabilize MBL and that are especially pronounced probably in 2D. And so we have been thinking about these things, and one idea, of course, what you could do is, since you are structuring the disorder pattern yourselves, you have control of what is shown onto the atoms, you could structure it in such a way that you have regions here where you exclude disorder, and the system becomes ergodic in these bubbles, thermalizing, and then you basically embed them in this disordered landscape, and you ask, how do these ergodic bubbles, can they grow in the system? Can they basically destabilize the entire system? So far we weren't successful in seeing anything of that, so it seems that if there are these avalanche processes, the timescales, at least for the disorder strengths where we have been looking, must be extremely long, must be maybe exponentially long in the disorder strength that we've been looking at. Okay, I want to talk about a final experiment, which is this bath coupling experiment, which I think is interesting, and the question is, what happens if you couple a disordered system to a system which does not experience the disorder? So one, let's call that the dirty system or the disordered lattice, and then we have the clean component. And they interact with each other through contact interactions. So if you think about these Hubbard models, you have these two spin components. The spin ups and ups interact with themselves. The spin downs interact with themselves. They're bosons, so this can happen. And then there's the interaction between the two spins. So this is where this clean atoms can actually see the disordered atoms simply through the contact interaction in the system. Okay. And then again, you can do the same spirit of experiments. You can, prepare the dirty component and the clean component in this charge density wave state. You can look how that evolves as a function of time, as a function of disorder strength, and the number of particles that you have in the clean bath versus the number of particles you have in the dirty component. So what are the outcomes that you could expect? I mean, just completely unbiased, there are three possibilities that you could have. Imagine one of the components is delocalized. It's a small bath. You bring it in contact with your localized system, and that might delocalize the entire system. So everything becomes delocalized. There could, of course, also be the opposite effect, that the localized system imposes localization on the delocalized system. So this would be some MBL proximity effect, what people call MBL proximity effect. So that could be an outcome. But in principle, there could be a third possibility, that both one stays delocalized and one stays localized. That's in principle also a possibility that you could have in the system. So this is why what I was asking Vincent, so here's the technical backup for how we do this, this kind of realization where one spin component sees the disorder and the other spin component does not see the disorder. And this is by using these so-called tune-out wavelengths, which we have for the different atoms. So you can go to a specific wavelength and look at the polarizability, which tells you how deeply your atom will be trapped or how much it will be experiencing a certain light field. And there are these very special situations like the one that you can see here, where you have a zero crossing for one of the spin components, and that means that even though you shine light onto the atoms, they don't see anything in the potential. The resulting potential is zero. Okay? While if you look at the same wavelength, the other component has a finite polarizability, and therefore sees a disorder strength in the system and sees the disorder potential. And this is this tune-out wavelength that we like to go to, that for our spin states works, for the one in Vincent's case does not work, unfortunately. And this is, of course, very nice, because you can really perfectly realize this situation even with low scattering rates, because the tunings are reasonably large towards the atomic resonances here at 795 and 780 nanometers in the system. So then to prepare the mixture, a controllable number of particles in this clean component or dirty component, we do the following. We start with one of the spin components, the one that sees the disorder state like this, and then we just do Rabi oscillations. We just drive Rabi oscillations between the spin ups and the spin downs, and now you can just stop your Rabi oscillation at any point in time and thereby have a controlled number of clean particles versus dirty particles in the system. You can just continuously tune the number of spin ups and downs in the system. And then we can just repeat the experiment that I've showed you before. And this would be the case where we have no atoms in the clean component, so there's no bath in the system. And we again see this plateauing, this localization happening. And then we see if we add particles into the system, already small number of particles reduces this steady state imbalance. And if we go to larger number of particles, the imbalance in the dirty component system, in the interacting system, actually also completely collapses to zero. So basically you delocalize the dirty component by bringing it in contact with this clean component in the system. So far we have evidence for the following, that we know for large enough baths, we indeed find this scenario here where the delocalizing component, the quantum bath, can delocalize the localized component. For small baths, it seems that localization seems to be able to persist, but we can't really distinguish between whether it's scenario 2 or 3. We haven't detected anything of a proximity-induced localization onto the clean component, where basically you would expect that to become localized because of the contact interaction with the dirty component. All right, so let me just finish off here this part and just raising some big questions, you know, that are connected now to MBL that people are struggling with. Is of course already what I told you, the whole notion of stability of MBL. Are we seeing eventually some relaxation? Are we seeing a pre-thermal phase? And there's only MBL, even in 1D, at much stronger interaction strengths than people had believed so far. Okay, so this is possible. This is what people would then call a pre-thermal MBL regime. It's, I think, still useful to think about it in terms of MBL, because the whole notion, the picture that, for example, Dima introduced to you, the picture of the L-bits and everything, would be still a good description of what's going on in large parts of this regime. But there would still be relaxation, but this relaxation would happen on time scales that could be exponentially long in the disorder strength. So it could be, you know, these could be astronomic timescales we're talking about. Now, I know, of course, you as theorists might be interested, you know, in terms of defining MBL as a phase. You want to know what's happening in the thermodynamic limit. You want to know what for infinite times, infinite system size, what's happening. But I would caution that no experiment is anyway ever going to be able to answer that question. So I don't know. I don't think we will ever be able to answer this question if there is maybe a true MBL transition here. Yeah, if there is one. But I think it's still interesting to understand what's going on here, and if there is this resonance physics that destabilize MBL, where could we look for that? Well, certainly not here, because here timescales are just so long that this thing for any experiment will look like this thing. But we could try to go more into this crossover regime and try to see more, look for observables. This is maybe what I would like to also give to the theorists. You know, let's analyze this regime more, and let's try to find observables which experiments can measure to show the presence of the physics of the resonances, which are abundant over here when they thermalize the system, and which become less abundant here when you go into this pre-thermal regime. This is just, okay, this is now basically, I would say, the most accepted picture. I don't know whether many people here, they might comment on that. They have their own view, but it is still contentious, so nobody knows if this is correct either. Okay. Yeah, I think as I said, with this localization length, there are of course very different notions of localization length in MBL, and I think the best one comes from this L-bit size of the L-bits, the effective size of the L-bits. As I showed you, this finite coupling to the bath is interesting by itself, but it's also super important because any experiment will always have this. So we need to understand that, and we need to understand at what timescales does it affect the system. Yeah, for the experimental part, I think, you know, we have to push to longer timescales. These 1000 tau timescales I showed you are really, I think, the longest that have been done in any of these interacting systems. On any platform. Maybe one can go an order of magnitude higher, but beyond that, I'm also not very hopeful that one can go to much larger systems, much longer timescales. We have larger systems now, so I do think we can make finite size scalings. That was what was introduced before. We have also much better homogeneous systems now, so I think it definitely would be interesting to go back to these much larger systems now and look at those questions again. All right. Do we still have a little bit? Or 5 minutes? Okay, so let me just show you just a really nice experiment of how you actually show the opposite. So I showed you showing localization in this MBL context is simple because in principle, from an experimental point of view, the only thing you have to find is show one observable that has a non-thermal expectation value, and show that it's in a steady state as good as you can under the conditions I said. You know. But of course, in the opposite case, you also might show, you know, has the system thermalized, and that's actually quite a little bit harder. And I want to show you a nice experiment from Markus' group how we actually showed that. And that comes back to the original point I made, you know, where we said, like, for typical physical systems without MBL, we have the reduced density matrix of the pure system being a thermal density matrix. And this is the von Neumann entropy of the reduced density matrix, and this basically then is the thermal entropy of the system. So thermal entropy in an isolated quantum system is von Neumann entropy of your reduced density matrix. Okay. So now, to show that that scenario is true in a quantum evolution, you have to show a few things. You want to show that under time evolution, the global system remains pure, remains in a pure state. So that the entire system is always in a pure state. Locally, the system looks thermal, and you want to have a probe that probes this von Neumann entanglement entropy. And the way, a very nice way how this was done, it goes back to a proposal by Dieter Jaksch and later work by Andrew Daly on how you can measure this von Neumann entropy in an experiment. And the idea is the following, and I don't have time to go into the derivation, so you can read the derivation in the papers. I just want to give you the idea. The idea is that you prepare two identical copies of your quantum system. You let them evolve, maybe, for example, but the initial state is exactly the same. They evolve under exactly the same Hamiltonian. And then you basically perform a local beam splitter operation on each of those bonds. So you just make a non-interacting beam splitter operation on each of those bonds in your lattice, for example. And then you measure the parity of the occupation of your lattice sites. And it turns out, if you measure the parity of these occupations of the lattice sites, you can estimate the Rényi-2 entropy of the system and determine the purity of your system. Okay, so this is a measurement of the purity of your system. And the Rényi-2 entropy, one can show, actually bounds the von Neumann entropy, so is a basically lower bound for the von Neumann entropy in the system. So this is also provable. So what you measure in the experiment is this Rényi-2 entropy via this Hong-U-Mandel, many-body Hong-U-Mandel interference effect. It's basically a many-body Hong-U-Mandel effect, if you are coming from quantum optics. And this allows you to measure this Rényi-2 entropy and say something about the purity. So here's what they did in the system. So they prepared two identical copies of this, let's say this mod insulator, small systems here, 6 atoms in the top row, 6 atoms in the bottom row. So these are the two identical copies. They are separated from each other. They now quench the system to large kinetic energy. So each of those 1D systems will evolve. Okay. And then they can do this many-body interference experiment, this Hong-U-Mandel experiment, to read out, make this copy to read out, measure the Rényi-2 entropy in the system. And for example, if you look at local observables after this, in the initial state, the occupation number, for example, the occupation number is 1 on those lattice sites in the initial state. If you look at the occupation number of the lattice sites after the time evolution, you actually, after this thermalizing time evolution, after this quantum quench, you actually find it follows nicely a thermal distribution, Poissonian distribution. And if you look, however, at the purity of the system from the Hong-U-Mandel experiment, you find that that actually stays constant throughout the entire evolution. So indeed, you showed that the purity of the system remains constant. You're in a pure system. But local observables evolve into the thermal state of the system. And this is actually nicely summarized here. Let me just show this as the final slide. So if you look at different subsystem sizes, you can look at a single site, look at the probability distribution of having the particles there after this quantum quench for different temperatures in the system. And you see how they nicely follow kind of thermal distributions. And you can choose whatever kind of ensemble you want, diagonal, microcanonical, canonical, eigenstate, grand canonical. They have small differences, but in principle, they all agree very nicely with the distribution that you measure. So locally, the system is thermal, looks thermal. But globally, as I showed you, it's still in a completely pure state. And just to look that you can do that also for different subsystem sizes. If your subsystem size is 3 particles here, this 3-particle system here to the left, you can see how that also agrees very nicely with a locally thermal distribution in your system, while you've also shown that globally the system is still in a pure state. So that's what you have to do to show thermalization and to show that this hypothesis in this quantum quench of really remaining in this pure state actually is true, that you're not coupling to any reservoir, you're not coupling to anything in the outside world, but you still show that locally the system evolves into this thermal state. All right, I think that's all I wanted to show you. Thanks a lot.